Hi, everyone. So welcome back to 165CL. We're in week 9, so we're almost done with the quarter. What we're going to keep doing is finishing up lab module 3. So today, we're going to take those samples that we went through all those different heat treatments with, and we're going to repolish that surface of interest so that it has a mirror finish and we can then go and study it. And then we're also going to perform hardness testing on these surfaces of these 3 different samples. And just a reminder, these samples all started the same. They're the same steel. We solutionized them the same way. And all we did is we changed how we sort of cooled and heat treated them. So they have different thermal histories. And after today, we'll have most of what we need. Our last thing to do next week will be to etch the surface and look at the microstructure to aid in our interpretation of this data we get today. So the first thing we need to do is go and create a nice perfect surface to study. We had polished these samples to get rid of all the machining marks on the surface. But once we did the heat treatment, we developed this oxide, which you can see on one of these samples, which hasn't been polished at all yet. So what we need to do is remove that with some of the same polishing steps. These 2 samples right here are shown after a rough polishing step, which you can see in this middle image. So here you can see those big scratches. They're gouges on the surface, but it's gotten rid of all of that iron oxide that's on the surface here. Okay. So this surface, it looks a little bit better. We can tell it's metal, but it wouldn't be good enough to move forward with. So if we tried to poke it on the surface, those indents would be roughly the same size as the scratches. So we wouldn't be able to measure good properties. And then if we etch that surface, we wouldn't be able to see the features we want to see. So we actually have to move down progressively to finer and finer sandpaper so that we can get a nice mirror surface on all of our 3 samples. I'm just showing one here where I picked it up and I tilted it. You can see part of my face in that sample surface. So this is truly a mirror-like finish. All right, so I went and made a video of myself working through these steps. So polishing these samples to this really fine finish, and then taking them and going to the indenter and doing some hardness tests, and then finally looking in the microscope and measuring indent sizes. So please go ahead and click on the link. It's either in the slides that are in the files page under Canvas, or on our homepage at Canvas, there's a link as well. All right, so I went and measured 10 different indents for those 3 samples. And for each of those indents, I took the 2 measurements of the indent width. Those are compiled in an Excel sheet that you can go and find under the Files tab on Canvas as well. What you're going to need to do, though, is manipulate those so that you can get hardness values. Just a reminder, the first step is for each of those 10 indents, for each of the samples, you're going to go and find an average diagonal length. And then you're going to use that to calculate the Vickers hardness. Again, the hardness is just a constant times the force divided by the length squared, okay? The only reminder or thing that's different is that when we did this experiment on the aluminum copper alloys, we used 50 grams force. They were pretty soft. We didn't need to use a lot of force to get an indent we can measure. These, we expect them to be a little stronger. So I went ahead and used a higher load to create the indents on the surface. I used 200 grams force. So make sure you put that in for F in this equation. On this slide, I'm just showing 3 example images. These are all taken with the 10x resolution microscope lens. So all the dimensions should be the same between these different images. I didn't manipulate them in any way. So you can even just notice that these indents look bigger for the tempered martensite and pearlite as compared to the martensite. So same load pushing on the surface, I'm viewing it with the same resolution and same magnification. I can notice that these are smaller indents here. So in this case, for example, I could see all 10 indents I put on the surface in one image. The same size image, I could only get 4 or 5 indents in that surface. I could go and measure them, and again, all of those data points are in that Excel file, but I just went and looked at the first indent that I measured, and you can even see that without analyzing all the data, these indents are much smaller than these ones, which are smaller than these ones. Okay. One other thing I wanted to point out, on the martensite sample, if you look very closely at these indents, there's a slight asymmetry to that indent. If I were to draw a line here, the region to the right of that doesn't look exactly the same as the region to the left of that. That's just a sign that perhaps our sample was tilted slightly with respect to where the indenter was coming in. It's not a huge deal here, and it actually isn't too bad, but I just wanted to point it out as something you could look at and notice if you're doing this yourself. So when I go in and calculate all my hardness values, and remember, I'd like you to do this yourself, I can go and get a value for each of the 3 samples and then plot this in different ways. And here I chose to just do it as a bar graph. So what you can see is the martensite sample is in the 600s of Vickers hardness. The tempered martensite is in the high 200s. And the perlite is in the mid 100s. So there's pretty large changes between these different samples. And that martensite is about 3 times, maybe 2.5 to 3 times stronger than this tempered martensite, and almost in more than 3 times stronger than this perlite. Okay, so the large difference, again, the only thing that's changed is they have different thermal histories. They started out as the exact same material. This little blue bar that I plotted here is just the standard deviation in the values that I measured. And just for reference, so our max hardness for the aluminum copper alloys, so this was the sample that was heat treated at an intermediate temperature for a long time, for a full day, was 117 Vickers hardness. So noticeably less than even this very coarse perlite that we made, okay? The last thing I wanted to point out is I also, in addition to our 10 indents with 200 grams force, I made a single indent with the largest force I could. This is a 1 kilogram force or 1,000 grams force in the 3 samples. And they're shown here on this slide. You can notice some of the same things, that the indents are larger for the softer materials, fine. But you can also notice some differences in what the surfaces look like. If you look closely around the indents, you can see some surface features here. These were perfectly smooth surfaces. So these deviations in that, what used to be a flat surface now, and these undulations are actually representative of the plastic deformation and the flow of material that's happening underneath the indent, okay? And just as another way to visualize this, if I go and draw and isolate the regions which have that plastic deformation, you can see that as I go from left to right and I go from a harder material to softer material, that region gets bigger around that indent. Okay. All right, so we have some data to interpret how the difference in our thermal history can give us different material properties and even some big changes in those material properties. And then again, the last thing we'll do next week is we'll take these same samples and we'll etch the surfaces so that we can see some of the microstructure and add to that interpretation of why those different mechanical properties exist.